It's easy to think that quantum mechanics is just a theory about tiny particles, nothing more. But what if I told you that it might predict that you can never truly die? Quantum immortality. Quantum theory tells us that the world behaves in ways that defy classical determinism, famously described by Einstein as God playing dice. Left to their own, particles don't have definitive positions or velocities. They are everywhere and nowhere all at once. In truth, quantum mechanics is perhaps best understood as a theory of superpositions. For example, an isolated electron does not have a sharp spin-up or spin-down state. Rather, it is quite literally in a superposition of both at once. It's only when we look at it that the electron seems to choose. This behavior is most clearly illustrated with the famous double-slit experiment. Gradually shoot just one electron at a time against a wall with two small holes in it, and you'll get an interference pattern on the other side. Somehow, even a single electron acts as if it travels through both slits at once, producing that interference pattern. Indeed, the electron acts just like a wave, with phase maxima constructively interfering to create peaks and minima combining into troughs. But if we put a detector on one of those holes, thereby allowing us to track which hole it went through, the interference pattern disappears and we just are left with two smudges. They now seem to act like particles. The consequences of this simple experiment are perhaps the most profound in all of physics. It deeply uproots our common sense intuition, and it reveals quite clearly that the universe is not what it seems. If you feel confused or perplexed by this, then, well, you're in good company. For even Richard Feynman, who helped develop quantum electrodynamics, famously stated, "I think I can safely say that nobody understands quantum mechanics." And so physicists and philosophers have argued for a century about what quantum mechanics really means for the nature of reality. One thing they do largely agree on is that prior to any measurement, the nature and evolution of these superposition states can be described like a wave. Indeed, we call this the wave function, first written down by Erwin Schrödinger 100 years ago. But the real question is, how does this quantum wave-like state suddenly transition into the more familiar classical particle-like behavior post-measurement? For decades, the dominant view has been the Copenhagen interpretation. That is, that these superposition states persist until they are observed, at which point they collapse down into a single sharp state with a probability given by the Born rule. That is, a probability given by the square of the wave function. This certainly produces exquisite agreement to experiment. Indeed, it is arguably the most precisely tested theory in all of science, verified to within parts per trillion precision. But it doesn't explain ontologically what's really going on. First off, it's important to say that most physicists reject the idea that wave function collapse in any way involves human consciousness. Instead, these measurements could simply be an interaction with the environment, such as a stray photon near one of the slits. But then here's the problem. Surely that photon then also becomes mixed up in this superposition, a combination of striking the electron and not striking it. Certainly, we know that superpositions are not limited to individual particles. Entire ensembles can be in a superposition too, in which case we describe them as being entangled to one another. In fact, that is the basis behind quantum computing, teleportation, and cryptography. So as our electrons from earlier proliferate out into the wider world, then surely too shouldn't this superposition state, this march of entanglement spread out too, eventually even encompassing human observers. But of course, the problem is, in our everyday life, we do not experience any kind of superposition effects, so surely something is missing here. This weirdness is most vividly elucidated with the infamous Schrödinger's cat experiment. Imagine a cat in a box with a bottle of poison that will crack open at a certain time with a 50-50 probability governed by the outcome of a quantum measurement, say whether an electron is spin up or down. Now, after the critical moment passes, the electron can be described as being in a superposition of both states. And since the measurement device is entangled with this quantum system, then so too must be the cat, existing in a bizarre superposition of being both dead and alive. Wave function collapse, via the Copenhagen interpretation, at first seems to resolve this paradox, but it comes with many problems. For example, why is it that the observer, be it a stray photon or the cat, or indeed we who open the box, are allowed to be considered somehow distinct classical entities, whereas the electron has to be considered quantum? Surely everything deep down is truly quantum. There's also no mechanism for this mysterious, unitary, and frankly ad hoc wave function collapse, and so not surprisingly, debate has raged for decades about what quantum theory really means.
I sincerely hope that this is the last time that I find myself here.
You just don't get it, do you, Jean-Luc? The trial never ends.
In 1957, Princeton graduate student Hugh Everett proposed a radical alternative interpretation. Put simply, the wave function never collapses, ever. Collapse implies that the other states in the superposition simply disappear and only one persists. Everett suggested that all possible outcomes of a quantum measurement occur, evolving in separate, non-interacting branches of reality. This so-called many worlds interpretation was, for a long time, largely ignored by the physics community, but in the last decade or so, it has risen to being a serious contender, championed by the likes of Sean Carroll, David Deutsch, and Max Tegmark. You know, Everett's idea is really pretty simple. He just takes the Schrödinger equation completely seriously. There is no collapse in that equation. And so that means that the electron, the box, the cat, you, me, indeed the entire universe are described by one gigantic wave function, often dubbed the universal wave function. In place of collapse, the many worlds interpretation explains the classical appearance of our macroscopic world by a concept known as decoherence. So the question is this: if the entire universe is in a superposition, then why don't branches interfere with each other like they do in the double-slit experiment? The answer lies in phase coherence. In simple systems, quantum waves stay in sync, and that allows them to interfere. But in complex systems, interactions with countless particles scramble their phases. The result? A clean split between worlds, known as decoherence. Subtly, this branching of realities is not an abrupt event. It evolves as the decoherence spreads, exponentially suppressing interference between different quantum branches. After decoherence, the universes can no longer have any causal influence on one another, so no, sadly you can't make a Council of Ricks. Yet, the number of universes here would be stupendous, because this branching would have been going on since the Big Bang itself and across the entire cosmos. You can even create new universes yourself using the Universe Splitter app. This is not sponsored, where you can base your decisions based off a quantum measurement made over in Switzerland. So in this branch of reality, I'm posting this video at 2 p.m, but in another, I posted it at 1 p.m. Both really happened. But if this whole idea of splitting bothers you, well, you're not alone. Theoretical physicist Bryce DeWitt is said to have visited Everett and praised him for the elegant mathematics of his idea, but told him that he was bothered by the gut feeling that he didn't feel like he was constantly splitting into parallel versions of himself. Everett is said to have coolly responded, "Do you feel like you're orbiting the sun at 30 kilometers per second?" "Touché," DeWitt said, conceding on the spot.
You think that's air you're breathing now?
In the quantum multiverse, your information might be proliferating across countless realities, but at least in this branch, you might want to limit the spread of your information, and that's where today's sponsor comes in, Incogni. Here's the deal. Your data is currency to many companies, such as your address, employment history, social media accounts, telephone numbers, and much more. These companies harvest, sell, and trade your information without your consent. Incogni is a fantastic service that I've been using for years. They go out and scour public databases for your personal info and then demand that that information be deleted, as is your legal right. And there's never been a more pressing time to have Incogni, because check this out. Since November, my Incogni dashboard shows a big spike in the number of deletion requests that they've made. To date, they have deleted my personal information from 678 databases, which would have cost me an estimated 508 hours of my time. Incogni is a great peace of mind service, and they're supporting this channel, so we're extra thankful for that. So to get started, head to incogni.com/coolworlds and use the code COOLWORLDS to get an exclusive 60% off their annual plan. Once again, that's incogni.com/coolworlds, code COOLWORLDS. Now back to the video. Amongst physicists, the many worlds interpretation has grown in popularity thanks to its rigorous treatment of the Schrödinger equation. But as the idea has gained traction, many have realized that it implies a bizarre and radical consequence. The idea can be best thought of as a game of quantum Russian roulette, and was popularized by Max Tegmark in his book, A Mathematical Universe. He describes a quantum machine gun, which can fire up to once per second depending on the outcome of a quantum measurement. Specifically, each time the gun is triggered, it places a particle in a superposition where it's equally likely to be in two states at once, for example, spin up and spin down, and then it measures that particle. If spin down, the gun fires and kills you faster than human perception, else it just makes an audible click, and it repeats this every second. Now, according to Everett, there will be two parallel universes after the first second, one where you're dead and the other where you're alive. In other words, there is exactly one copy of you that has perceptions and a stream of consciousness both before and after the experiment. Now, since you can't experience not being alive, then the prediction is that you will hear an audible click and survive this measurement with 100% certainty. And of course, what's really bizarre is that you could sit there and experience dozens of clicks in a row, somehow surviving time after time. After 40 sequential clicks, the Copenhagen interpretation says that there's a 1 in a trillion chance that you'd still be alive. But Many Worlds says that there will be, to 100% confidence, a version of you that survives this extraordinary sequence of events, and that you would thus be able to conclude that Everett's idea was right all along. In effect, then, you will be able to prove that the Many Worlds interpretation was correct. But it would be a strangely private proof. For in the other trillion universes, everyone else would just watch you die, wondering why you would do such a thing. They would not see this proof, and thus this experiment fails to convince the rest of the world. Although Hugh Everett never wrote about this idea, Eugene Shikostev's biography states Everett firmly believed that his many worlds theory guaranteed him immortality. His consciousness, he argued, is bound at each branching to follow whatever path that does not lead to death, and so on ad infinitum. Sadly, on our branch at least, Everett had a difficult life. After widespread rejection, he became withdrawn, failed to get an academic job, drank and smoked too much, and eventually died of a heart attack at age 51. Now, Tegmark is very clear that this is not an experiment that he recommends conducting for yourself at home, and I want to emphasize that point here too. It would be incredibly stupid, foolish, and idiotic to engage in this experiment at home, and I think it will become increasingly clear as to why I think that throughout the rest of this video. But hypothetically, Tegmark argues that there are 3 criteria needed to make this macabre experiment really work. Criteria 1, the random decisions must be quantum. 2, it must kill you or make you unconscious on a timescale shorter than that which you can perceive. And 3, it must really kill you, not just very badly injure you. Satisfy those 3 criteria, and the argument goes that you would somehow miraculously survive time after time.
Yes! I am invincible!
In a 2001 lecture, philosopher David Lewis expanded upon this game of quantum Russian roulette to broad immortality. He reasoned that the entire universe is ultimately governed by quantum events, and thus all causes of death satisfy Tegmark's first and third criteria. For example, if a car is about to hit you on the road, there is a stupendously small probability that the vehicle will quantum tunnel straight through you without causing any harm. And according to many worlds, a version of you must survive such encounters. Indeed, if David Lewis is correct, then eventually each of us will one day gain personal evidence for many worlds, for we will seem to always escape life-threatening car crashes, survive health scares, and eventually outlive our friends and our family. Tegmark isn't in alignment with David Lewis's position, though, via his second criterion, because most causes of death are not faster than our perception timescale. They are more typically a slow deterioration of our mental faculties, something that we could gradually experience. But even this point, Lewis seems to have anticipated with a frankly dark and terrible prediction for us all. For Lewis concedes that, in general, you will indeed deteriorate, but all you need to do is survive each moment, not necessarily come out the other side particularly healthy. Over time, you would accumulate ever more deterioration, like the Struldbergs from Gulliver's Travels or the protagonist of Death Becomes Her. Lewis writes, "As you survive deadly danger over and over again, you should also expect to suffer repeated harms. You should expect to lose your loved ones, your eyes and limbs, your mental powers, and your health. Eternal life on such terms amounts to a life of eternal torment. Is this the fate that awaits us all?"
My body is broken. You have to let me go.
Since quantum immortality is so personal, a good question to ask is whether our own experiences of the world are consistent with its predictions. So let's revisit the first half of Tegmark's second criterion, that you must die or lose consciousness. It's already non-trivial for Tegmark to equate those two states, but I suppose the reasoning here is that in neither state can you perceive anything. Physicist Anthony Aguirre latches onto this point in his book, Cosmological Koans, considering what it means when we are anesthetized or even asleep, experiences that we can all attest to. One might argue that we should always live on the branch where we stayed awake all night, every night, because the branches where we sleep are imperceptible to us. But of course, even asleep, there is a reduced form of consciousness, such as dreaming. Yet more, those reduced states of consciousness are not permanent. Skip forward 8 hours in both branches and you would find a conscious version of you. Another line of anthropic attack is to try and invoke the mediocrity principle. If we really live forever in increasingly decrepit states, then there will be far, far more years of you alive in that state than the relative youth that we all enjoy now. In fact, in the story of your existence, it would be incredibly unlikely that you'd happen to inhabit a moment during your, let's call it, normal age life, rather than these Struldberg years. I think that this does make for a compelling counter-argument, but it is the same kind of reasoning used by the doomsday argument and the Boltzmann brain discussions, which can all be challenged on the issue of reference class. Perhaps your future state is very different from this current state, and thus, in fact, you do occupy a mediocre position of your current reference class, that is, being youthful. Despite our best efforts, these concerns can't deliver a knockout blow to quantum immortality, but if we revisit Lewis's argument, we can discover a questionable assumption that challenges the entire idea, an assumption about the way the universe works.
If there's nothing wrong with me, maybe there's something wrong with the universe.
A central line of reasoning in David Lewis's case for immortality is what he calls the corrected intensity rule, and it really speaks more broadly to a topic of constant tension in discussions of the many worlds interpretation. Let's say a life-threatening quantum-triggered event occurs with 4 distinct and equally likely outcomes, in which you perish in 3 of them. Now, in the Copenhagen interpretation, we would simply assign a 25% probability to each outcome occurring using the Born rule, and indeed, only one will occur. But in many worlds, all 4 happen with 100% probability. Of course, if everything happens to 100% probability, then the theory really lacks any predictive power, and thus Everettians get around this by saying that each reality occurs with a 25% measure of existence, or a 25% intensity, again taken from the Born rule. Now, your consciousness can surely only inhabit one reality at a time, and thus you might reason that there is a 75% chance of you dying in this grim scenario, even in the many worlds interpretation. But Lewis's trick here is to discard all of the cases where you die because, and I quote, "Death is oblivion. The experience of being dead should never be expected to any degree at all, because there is no such experience." This act of discarding branches where you die and then renormalizing is what Lewis calls the corrected intensity rule, and it is pivotal to the case for quantum immortality. But many thinkers take issue with this sleight of hand. For example, philosopher David Papineau writes, "It is by no means obvious why Everettians should modify their intensity rule in this way, for it seems perfectly open for them to apply the unmodified intensity rule in life or death situations, just as elsewhere." Many worlds champion David Deutsch also pushes back here, writing in his book that this way of applying probabilities does not follow directly from quantum theory as the usual one does. It requires an additional assumption, namely that when making decisions, one should ignore the histories in which the decision maker is absent. My guess is that this assumption is false. In other words, when the universe makes it split, there's by no means a guarantee that you will take the path in which you survive.
I didn't think it would end this way.
End? No, the journey doesn't end here. Death is just another path. One that we all must take.
I think Papineau and Deutsch make great points. It is indeed wholly unclear that we can discount death branches in the way that Lewis prescribes. But neither of them can falsify Lewis's claim either. Sure, he's added an extra assumption here, but that doesn't mean that it's wrong, and it stems from a reasoned perspective. All the quantum weirdness kicking around makes it difficult to know what's real and what's not, so let's instead try to think about more conventional analogies. So leaving aside generalized immortality just for the moment, let's come back to the more pointed case of the quantum Russian roulette example that Tegmark described earlier. A thought-provoking analogy to this experiment is to imagine a kind of Star Trek-style transporter that beams you up and then rematerializes you somewhere else. Before the beam out, there's one of you, and after the beam out, there's one of you. Certainly in Star Trek, most characters don't seem bothered by this process, so let's assume that it's perfectly safe and not a death machine then. But imagine instead if it created 2 versions of you by some kind of transporter malfunction. Again, strictly in terms of your own survival, this really shouldn't bother you. You will persist, although the ethics of cloning you probably are a point of concern. This splitting is exactly analogous to what happens in many worlds. Your consciousness, you, whatever you want to call it, can only occupy one body, and yet both versions of you would insist that they were real. So which version of you really is you? Now, as a final twist, consider that one of those 2 rematerializations fails and leaves behind a gory mess on the transporter pad. Now, you might reasonably be disturbed at the prospect of stepping on that transporter pad because there'd be a 50% chance that you would die, right? But on the other hand, that dead version of you never even materialized enough to experience consciousness, so surely it's impossible for you to become that puddle of flesh. And we can take this a step further and say that the crew never even attempted to rematerialize the second beam. The malfunction was detected and the file deleted inside the computer. In this case, aren't we exactly equivalent to the original scenario of a one-to-one beam out, in which case few objected? Now, in fairness, I promised you a conventional analogy and then started talking about transporters, so the fact we don't understand how such a machine would truly work perhaps only adds more confusion to the mix here. So consider instead a classical analogy described by Sean Carroll in his book, Something Deeply Hidden. Okay, so Lewis's whole argument is that you really shouldn't be bothered about the branches where you die because you can't experience that. But Carroll strongly disagrees with that. After all, if someone snuck up behind you with a gun and instantly killed you, you should not be okay with that. The fact that you can't experience being dead is completely beside the point. It is totally reasonable to not want to be killed regardless.
The reason why we don't want to die is not just that we will experience pain, but that sort of prospectively, right now, the idea of being dead in the future bothers me, right? Mm-hmm. Like, if someone said, you're going to die in this and that date, it might be useful information, but I'd be sad, right, if that date was soon. And I think the same thing is true in the quantum immortality experiment. I don't buy the move that says, well, in all the branches where you're dead, it doesn't matter because you're dead. You don't feel anything.
Unfortunately, David Lewis passed away soon after giving that lecture, which spawned this whole quantum immortality discussion. But I imagine he would have pushed back against Carroll's scenario as being a very different beast, because in that case, you definitely do die. Whereas I think Lewis would maintain that in the quantum picture, your stream of consciousness continues uninterrupted. It's definitely reasonable to be disturbed by the finality of Carroll's classical experiment, but Lewis's whole point is that in the quantum version, there is no finality. It was Max Tegmark who really popularized the quantum Russian roulette experiment, but it's interesting to note that he somewhat walked back on the idea that you'd really survive such a thing. As we noted earlier, he points out that most forms of death fail his second criterion of occurring on a timescale faster than human perception. But I think to me, it is deeply unclear that this criterion would truly safeguard your continued survival. In particular, philosopher Charles Sebens has argued that the timescale is irrelevant. After the quantum gun fires, the universe has already split into two, even before the bullet reaches you. Both versions are credibly what you might call you, and thus you will die in one of them. I think that point alone makes for a very compelling reason as to why you should never try this experiment, because in truth, no physical process is truly instantaneous. But Tegmark and others are also bothered by the thorny issue of how many worlds deals with probabilities, or really measures of existence between the different branches. I think that this is the issue more than any other that critics of the many worlds interpretation often bring up. How is it possible that all of these outcomes occur with 100% probability? For example, after a large number of Russian roulette experiments, the number of worlds in which you survive is astronomically small. Shouldn't this bother you? Physicist Lev Weidman agrees, writing that the large measures of the worlds with dead successors is a good reason not to play. But in truth, aren't we all already low measure? After all, since the Big Bang, countless branchings have happened, and the number of worlds in which you happen to be born and be here would be an incredibly small fraction. And so, by this logic, you shouldn't even really be here right now.
We've all been dancing around the basic issue. Does Data have a soul? I don't know that he has. I don't know that I have. But I have got to give him the freedom to explore that question himself.
And so we finally come to it. This bizarre concept is as much about the theory of the mind as it is about quantum reality. Because a latent issue throughout this entire discussion has been, what does it really mean to talk about you, your consciousness, your identity, your selfhood? This is quite possibly the most difficult question that humanity has wrestled with throughout the ages, and as you might imagine, there's no agreement. My Columbia colleague, Brian Greene, thinks of it this way. Each copy is you. You just need to broaden your mind beyond your parochial idea of what you means. Each of these individuals has their own consciousness, and so each of them believes he or she is you. But the real you is their sum total. In contrast, Lev Vaidman takes a more pragmatic view, stating, there are many different Levs in different worlds, but it is meaningless to say that there is another I. There are, in other words, beings identical to me at the time of splitting in these other worlds, and all of us came from the same source, which is me right now. Philosopher David Wallace pries open this view a little deeper, arguing that the sense of I can only make sense if identity is confined to a single branch of the quantum multiverse. Since it's not clear how this can happen, Wallace concludes that we may have inadvertently demonstrated that many worlds is not a conceit of multiple selves, but rather it is dismantling the entire notion of selfhood. It denies any real meaning to you. You know, I can't help but be reminded of another debate raging in quantum theory regarding the so-called black hole information paradox. You can watch our early video to learn all about that, but it's an example where two seemingly sound theories, quantum mechanics and general relativity, collide and imply inconsistent results. Here, quantum mechanics collides with selfhood, and once again the result seems to be that there is something amiss in our fundamental understanding. Indeed, cosmologist David Aguirre argues that the entire debacle can be characterized as a reductio ad absurdum against our current understanding of many worlds and the theory of the mind.
For that one fraction of a second, you were open to options you had never considered. That is the exploration that awaits you. Not mapping stars and studying nebula, but charting the unknown possibilities of existence.
On the 27th of October 1962, at the height of the Cuban Missile Crisis, a Soviet submarine near Cuba was surrounded by American destroyers and so had to dive to avoid detection. Whilst unable to contact Moscow, the Americans dropped practice depth charges to try and signal the submarine to surface. But the Soviet captain thought that these were real and ordered his crew to launch a 10-kiloton nuclear weapon against the Americans. His political officer agreed, but the second officer, Vasily Arkhipov, did not and managed to talk his captain down from firing. World War III did not happen that day, nor since, because, of course, if it did, none of us would likely be here. In the many worlds interpretation, we could never live on a branch where that happened, because we'd be dead. Indeed, perhaps all of history is a sequence of improbable events that somehow conspired to lead to you, because in branches where they didn't, you aren't there.
What happened?
Instead of firing, they suddenly disarmed and canceled.
Fate. Protects fools, little children, and ships named Enterprise.
I think it's easy and a bit lazy to dismiss the immortality concept because it feels wrong or we just don't like it. But it's harder to come up with a fully rigorous dismissal of it and hold on to the many worlds interpretation. Ultimately, these kinds of Gedanken experiments help us to see where we need to do more work, where our understanding hits the end of the road. And like the information paradox, I think that there is something profound in this idea, a lesson for us about who we really are and the nature of reality. Personally, even if many worlds is true, I think Lewis's idea of immortality as Struldberg's is hard to swallow. After all, many worlds doesn't allow for anything to happen, outcomes still emerge from systems governed by physical rules. Yet more, at least to me, the whole notion seems to run afoul of the fact that it would be much more likely that I would currently inhabit a much older state than my present one. But there is a silver lining to it all. For in many worlds, even if we eject the whole worry about who is really you in these multiple branches, certainly in these other branches, doppelgangers of you and I would be there, would be living their lives. And even critics of the quantum immortality argument, like Peter Lewis in his book Quantum Ontology, agree with this logic, writing, "Certainly, the many worlds theory has the following consequence. At any future time, there is a branch containing a living successor of you." So maybe, out there, somewhere, Hugh Everett is still alive at 94 years old, perhaps surrounded by his great-grandchildren and his physics Nobel. David Lewis has just popped over for a friendly game of chess and to continue their debate on quantum immortality. And amongst these other branches, we might indulge to imagine all of our hopes and dreams transpiring, our aspirations for a better world, a happier life. And even though we could never access those island universes where we made different choices, where our loved ones lived longer, where history played out differently, they do exist. It proves to us that such dreams are realizable. And I think that can be a tremendous source of inspiration and comfort. So, until next time, stay thoughtful and stay curious. Thank you so much for watching this video, everybody. I hope you enjoyed it. If you did, be sure to hit that like and subscribe button. It really does help us out. And I want to just give a quick thank you to our latest supporters, that is Drew Aaron and Garrett Thompson. Thank you so much, guys, for your support. If you too want to become a supporter to my team, the Cool Worlds Lab, then you can use the link up above and down below. That's coolworldslab.com/support. So until next time, have a great one out there.